Hello world, my name is Kaitao Zhan from Stony Brook University. Today I am presenting my paper, DeepMTL, Deep Learning-Based Multiple Transmitter Localization. This presentation will be in 5 sections: Introduction, Problem, Solution, Evaluation, and Conclusion. For introduction, let's begin with radio frequency spectrum. The RF spectrum is a limited natural resource in great demand. The United States recently frees up 100 MHz previously military-occupied mid-band spectrum. Also, the US proposes the shared spectrum paradigm to increase spectrum utilization. Software-defined radio, or SDR technology, gives people easy access to RF spectrum, both receive and transmit. So here comes the potential security threat, where selfish users can transmit data on shared spectrum without authorization. Our goal in this paper is to find out all the unauthorized transmission, harnessing deep learning. So this explains our title, DeepMTL, Deep Learning-Based Multiple Transmitter Localization. Now let's illustrate the problem of multiple transmitter localization. We have a geographical area with a coordinate system. There are multiple transmitters in the area, and we wish to estimate the location of the transmitters. To accomplish this, we deploy a distributed set of sensors. The sensors will sense the wireless channel of interest and process the wireless signals. Then sensors compute the received signal strength. Then the sensors will upload the received signal strength to a spectrum manager in the cloud. The spectrum manager in the cloud will use some localization algorithms to estimate the location of the transmitters. Now let's formally define the MTL problem and list the challenges. Consider a geographical area. Assume a single channel. We distribute a set of crowdsourced sensors that report RSSI. There are multiple transmitters, including both legal and illegal ones. The definition of MTL is, given the observations from the sensors, localize all the transmitters present. There are 2 main challenges. The first one is that the sensors receive only a sum of the signals from the multiple transmitters transmitting simultaneously. The challenge here is that the sensors cannot separate the powers received from different transmitters. It only receives a sum. The second challenge is that there are multiple transmitters to localize, and some of them might be close to each other. The difficulty here is that when 2 transmitters are close by, it is hard for the algorithm to distinguish whether it is actually 2 transmitters close by or just a single transmitter. Now let's compare our DeepMTL with the prior work. The first one is Splot from Mobicom 2017. It is a logistic regression-based method. The limitation is that it cannot localize 2 nearby transmitters. The second one is our own MapStar from IPSN 2020. It is a Bayesian-based method with some divide and conquer techniques. The limitations are it has high computational cost and incurs a high latency. The third one we're comparing with is DeepTX Finder from ICCC in 2020. It is a deep learning-based method. The limitations are that the number of CNN models is linear to the number of transmitters, which makes the solution not scalable to the number of transmitters, and also looks inelegant. And the results doesn't look good enough. Now this is our DeepMTL from WoWMoM 2021. It is also a deep learning-based method. In contrast to DeepTX Finder, our DeepMTL has a constant 2 CNN models, no matter how many the number of transmitters are. So it is scalable with the number of transmitters and makes the solution looks elegant. And of course, the results are a lot better. Section 3 is Solution Overview. Let's take a look at the input, output, and the architecture. The input is a list of tuples, where each tuple describes a sensor's location and the received signal strength identifier. The output is also a list of tuples, where each tuple describes the location of the transmitters. The DeepMTL in the middle is the magic that turns the input into the output. On the right side is the architecture of the solution, where we deploy some crowdsourced sensors that sense the data from the transmitters. The sensing data will be uploaded to a spectrum manager cloud. It first goes through a database and then goes to the DeepMTL, which does the magic and outputs the estimated location of the transmitters. This slide and the following slide are the two most important slides in this presentation. These two slides describe the core idea of this paper, which is we proposed a two-step CNN-based method. So DeepMTL is essentially two steps. Step one is it represents the input sensing. Step one is it represents the input sensor readings as an image. Then it apply an image-to-image translation CNN model. Then it goes to step two, where it applies an object detection CNN model. And then step two will output the estimated location of the transmitters. Now this is an illustration of the two-step core idea. First, we turn the sensor readings into an image, which looks like this. Goes through the first CNN, the image-to-image translation model, and we get a distribution of transmitter locations, which is an image of peaks. Then this image goes through the second CNN, which is the object detection, and we view the peak as an object, so object detection becomes a peak detection. And the result is that the object detector will put a bounding box on the peak, and we will have the coordinate of the bounding box. Each bounding box describes a peak. Now this is taking a closer look at what a bounding box is. Now let's take a deeper look into the input and output representation. In this area, we have some sensors and transmitters. The input representation will decode the sensor information. So we have a grid, and a sensor will fall into a cell of the grid. We will assign a value to the cell. The higher the sensor readings, the higher the value. Now let's take a look at the target representation. There are three transmitters here. So in the target representation, we have three Gaussian peaks, where each Gaussian peak represents a transmitter. Now let's take a look at the model. The model is called send to peak. The model has 4 layers, layer 1, 2, 3, and layer 4. The 4 layers has 8 channels, 32 channels, 8 channels, and 1 channels respectively. If we look at the entire architecture, we will see that it is pretty symmetric. In the end, we'll have an output image, and we compare this output image with the ground truth. Then we do a pixel-wide L2 norm as the loss function. Now let's take a look at step 2, peak detection. Given an image of transmitter distributions, which is the output of step 1, we want to find the peaks, where each peak denotes a transmitter. Look at the figure on the right side. We see that there are 5 peaks here, and each peak denotes a transmitter. A simple way of doing it is use a local maxima based method, which is maximum picks a value within a circle of a certain radius. The problem of this is that setting the radius value and the threshold for peaks is ad hoc, which makes it very difficult to tune. So we need a more intelligent method, and we resort to deep learning. Step 2, peak detection. We are going to utilize YOLO, you only look once, an advanced and popular object detection method. In the computer vision community, object detection is localizing objects in an image. A transmitter's distribution is a peak. We view a peak as an object. Then, the idea of applying an object detection method naturally comes. We tailor the YOLO v3 and introduces YOLO v3-cust. So this is an overview of the pipeline. On the right side, the output of the YOLO v3 cust are the coordinates of the center of the red bounding boxes. So if you look here, there are two transmitters x1, tx1, and tx2. And this is the output of send to peak. The YOLO v3 cust takes this as the input and output two bounding boxes. So we can see here there are two bounding boxes here, and it will gives us two coordinates of the center of the bounding box. Now let's take a look at the model, the YOLO v3 cust model. The original YOLO v3 is pretty large. It has 106 layers. It has a darknet backbone, which is trained on ImageNet, and also have three YOLO layers, YOLO layer 1, 2, and 3. Based on the original YOLO v3, we did 4 customizations, where 2 of them are major. First, we skipped the first 2 YOLO layers. Skipping means while the YOLO layer is still there, we don't use it to predict the bounding boxes. The second major customization is that we change the anchors from rectangles to squares. We are able to do this because we kind of already know that the square anchors are enough for peaks. The higher level idea of the customization is to make the model's life easier based on some prior knowledge we have. Section 4 is all about the evaluation. Let's begin with the setup. The data we used for training the deep learning model is generated using a simulator called SPLAT. We generate around 100K samples for training and 20K samples for testing. The performance metrics we use are localization error, the miss rate, the false alarm rate, and the running time. We use a geographical area of 1 kilometer by 1 kilometer. We use a 100 by 100 grid, so each cell is 10 meters by 10 meters. The default parameters in our experiment is the number of transmitters is 5, and the sensor density is 6%, which there are 6 sensors deployed in every 100 cells. Now let's compare the localization error of 3 different step 2 methods, sharing the same step 1. First, we have DeepMTL, which is the proposed method in this paper that utilizes a customized YOLO v3 in the step 2. And we have 2 inferior alternatives. One is DeepMTL-YOLO, which uses the original YOLO v3, and DeepMTL-peak, which uses a naive peak detection method. Here is the result. This is plotting the cumulative distribution. From the plot, we observe that the red line describing the DeepMTL is the best. When we compare the red line and the blue line, we can conclude that the customization for YOLO v3 is really helping the object detector. When we compare the first 2 methods with the last method, which is DeepMTL-peak, the orange one, we see that a deep learning based method is really better than a non-deep learning based method. So deep learning is more intelligent. Now we compare the localization error while varying the number of transmitters. We will compare our proposed DeepMTL with the other 3, MapStar, Splot, and DeepTX Finder. Here is the plot. We observe that when the number of transmitters are 1 or 2, MapStar has the lowest mean localization error, while the number of transmitters increase to 3 or above, then DeepMTL has the lowest localization error. When we compare DeepMTL and MapStar, we will see that DeepMTL is better at handling many number of transmitters. Both DeepMTL and MapStar are significantly better than the 2 others, Splot and DeepTX Finder. Now we compare the false alarm rate and the miss rate while varying the number of transmitters. First, I want to note that we stack the false alarm rate on top of the miss rate and get 1 bar. The lower the bar, the better. From the plot, we observe that when the number of transmitters is 1 or 2, map star is the best. When the number of transmitters increases to 3 or more, then DeepMTL has the lowest summation of false alarm rate and miss rate. Again, we can conclude that DeepMTL is best at handling many number of transmitters. We switch to varying the sensor density. Sensor density is also an important factor. Still, we compare the localization error, false alarm rate, and miss rate. So we look at subplot A. We observe that when the sensor density is 6 or below, DeepMTL has the lowest mean localization error. When the sensor density increases to 8 to 10%, then DeepMTL and MapStar have very similar mean localization error. Both DeepMTL and MapStar are significantly better than the other two, Splot and DeepTX Finder. Now let's look at the subplot B. When the sensor density is 2%, all 4 algorithms performs pretty bad. When the sensor density increases to 4 or above, then DeepMTL performs the best in terms of the summation of false alarm rate and miss rate. And again, DeepMTL is best at dealing with multiple transmitters when the sensor density is sufficient enough. Now let's compare the running time with varying number of transmitters. Here's a table. We observe that MapStar is the slowest. It is in the order of tens of seconds. Then comes Splot. The runtime is in the order of seconds. Both DeepMTL and the DeepTX Finder are very fast when doing the inference. DeepMTL's runtime is in the order of 10 milliseconds, while DeepTX Finder's runtime is in the order of milliseconds. DeepMTL is 1 order of magnitude slower than DeepTX Finder because DeepMTL has a 106-layer customized YOLO v3. The deep learning-based methods are significantly faster than the non-deep learning methods because they utilize a GPU where there are thousands of cores running at the same time. Now let's compare DeepMTL with DeepTX Finder. The question is, both are deep learning-based methods. Why DeepMTL is significantly better than the DeepTX Finder? The answer is because DeepTX Finder cannot accurately predict the number of transmitters, but DeepMTL can, with the help of an advanced object detector from the computer vision community. Now is the conclusion. We designed and implemented a novel 2-step deep learning-based approach named DeepMTL for the multiple transmitter localization problem. The evaluation shows that our DeepMTL outperforms the prior work by a large margin. Thank you for listening, and feel free to ask any questions. This paper and slides are available at my website. The video of this paper is available at my YouTube channel, and the code is open source at my GitHub. Thank you very much.